Okay, so work and energy. What comes to your mind when you hear both of these terms? For work, it might be pushing a rock up a hill, which also isn't wrong. And for energy, it might be the stuff that powers up the light bulbs in your house or wherever you see light bulbs. But really, what do you think work and energy mean? In common? Well, let's go on these topics one by one. Let's go on energy first. Energy is the quantitative property that must be transferred to an object to perform work or heat onto the object. There's so many examples of energy. I'll give you one. So the first one would be using batteries to power up a flashlight, since the energy from the batteries goes into the flashlight. As seen, energy can be transferred from the batteries. However, energy cannot be created, and energy cannot be destroyed either. If you were to destroy energy, it would be impossible because there is this law that science follows. This law is called the Law of Conservation of Energy, created by Julius Mayer in 1842. This law says that you can't create energy or destroy energy. I'm going to be talking about two topics, which are kinetic energy and thermal energy. So first of all, let's take a look at kinetic energy first. So what is kinetic energy? Kinetic energy is the energy that an object has because of its motion. So to make something clear is that if you want to make something move faster, particularly like a car or an object, you gotta use a little force. You gotta push it to let it move forward. It's logically, you gotta push it to move forward. So after energy has been transferred to the object will accelerate with the new constant speed. But how do you calculate kinetic energy? Consider work and force. W equals F times D. If there was a box, let's name it M, mass, being pushed through D, which is the distance along a surface that were parallel to each other, that we have the formula M times A times D. Acceleration, which is the substitute known as distance, initial, and final velocity. So let's write this down. Basically, when the net amount of work is done on a particular object, the quantity 1/2 mv squared, which we call the kinetic energy K, changes. Now let's write down the formula of kinetic energy. K equals 1/2 times m times v squared. Alternatively, one can say that the change in kinetic energy is equal to the net of work done in an object or system. This is the work and energy theorem. Potential energy. It is basically the stored energy inside an object, the exact opposite of kinetic energy. Potential energy is the energy that an object has in a system due to how it's arranged. M is the mass, h is the height, and then G is newtons per kilograms. Here's a simple illustration to give the difference between potential and kinetic energy if you're feeling kind of lost. An air in the balloon could be described as potential energy, and when the balloon is released, air from the balloon goes out and then the balloon goes upward, which we call kinetic energy. So let me give you a few more examples of Kyle holding dumbbells, which also has potential energy. Water behind a dam that holds potential energy because it is holding water behind a dam. And another example is a roller coaster. When you have cars on the tippity top of a roller coaster, it has potential energy and it must store enough potential energy for it to make the loop at the bottom. That's how roller coasters work, according to potential energy. Let's move on to gravitational potential energy. The gravitational potential energy that is in a stored object is the gravitational attraction to the Earth and the object. So it's basically the force of gravity of the Earth pulling things inside. So let's say Kyle has 2 bricks. He has 1 brick on the floor, and then he has another brick in his hands. The brick on the floor and the brick that he's holding, the one on the floor has no movement, it has no gravitational potential energy, but the one he's holding has gravity pulling it down, so it has gravitational potential energy. Now, let's say we have Kyle pulling this metal rod down with something attached to it with the end. So if the force were to be removed, the object will fall back down and the gravitational potential energy would be transferred back. Now let's move on to mechanical energy. It is the sum of potential and kinetical energy, giving it a really simple formula, which is EM equals EP plus EK. Let me elaborate on that. EM here is mechanical energy, P is the potential energy, and K is the kinetic energy. The only forces here are conservative, like gravity and springs. Forces that are non-conservative, such as friction, cannot have mechanical energy. Let's look at this example. Kyle decides to go golfing on the moon with an acceleration of 1.625 meters squared. And then the ball bounces at a club at 45 degrees, going 20 miles per second horizontally and vertically, with a total velocity of 28.28 miles per second. How high did it go? So first of all, we must apply the principle of conservation of mechanical energy, so we can solve for the height and h, and we got to note that the mass cancels out. So EM equals 1 over 2 mv squared plus mgh. Now we start solving for the gravitational potential energy, and then we got to write down 28.28, which is the total velocity of it, and then divided by 1.625 miles per second squared, and we get 123 meters. Okay, so let's get things a little heated up with thermal energy. Thermal energy is energy within an object that interferes with temperature. Examples of thermal energy could include heat being transferred to a heater, or the sun warming up Earth since the radiation waves go to Earth, thermal energy, and baking cookies in an oven since the radiation waves, thermal energy from the oven goes into the cookies, making them yummy and for us to eat.